This PowerPoint is over conservation of energy. Now, types of energies can be categorized into two different types. You got conservative energies, which is sometimes called mechanical energy. These are types of energies that you can increase or decrease these amounts. And then you have non-conservative energies. Non-conservative energies usually are contributed to like outside work that's being done on the system. So those are energies that either they constantly increase or they constantly decrease. We'll get to those in a second. So the types of conservative energies that can increase or decrease are referred to as kinetic energy, gravitational potential energy, spring potential energy, or rotational energy. Now, these types of energies, you can, kinetic energy deals with how fast you're going. So if you increase your speed or decrease your speed, you can increase or decrease kinetic energy. Spring potential energy, for example, is when you stretch a spring. By stretching the spring, you increase your spring potential energy, and then you release it when you let go of it. And then rotational energy, when objects are rotating, they can increase or slow down and decrease the rotational energy. So those are all the conservative types of energies, because those types of energies can either increase or decrease. Now, non-conservative energies are type of energies that only go in one direction. For example, an applied force. So if somebody is pushing on a force or pushing on an object, that's applying a force, and then that force does work. It does actually what's referred to as positive work. So it puts energy into the system, but it only goes in one direction. That applied force can't take energy really out of the system. So an example of like thrust or chemical energy, these are types of energies that if you think of combustion is a great example of chemical energy. Once that energy is released from gasoline that's burned, then that energy is gone and you can't get it back. So it always does positive work, and you lose that energy to chemical. Now, friction is another type of energy, usually called dissipated, and it's caused by heat and sound. This is your negative types of energy, so you lose this type of energy in your system. Friction takes energy out because it does work on your system to slow it down, so it takes that energy away. But friction doesn't really add energy back to the system, so it only goes in one direction. So these are effectively your two types of energy, your positive work and your negative work that's done by outside forces that do non-conservative energy. Now, in conservation of energy, the definition of conservation of energy says that in a closed system, energy will transfer from one type to another, but the total amount of energy will not, the total energy will not increase or decrease. So you don't lose any energy, you don't gain any energy as long as it's a closed system. Now, the purpose of a closed system is to say that there's no outside net force. There's no work being done on the system or by the system, that all the energy that's inside the system is going to stay inside the system, but it just transfers from one type to another. So if you can kind of think of this as buckets of water. So I got my example here. I've got gravitational potential energy and kinetic energy. So if I pour water out of the bucket into another, then that's transferring energy from one type to another, but we don't lose any of that energy. So while the energy transfers, the energy is going to be conserved even though it's in different types. Now, the next one, if we spill water, then that's referred to as negative work. We lose energy out of the system. So just like spilling the water out, that's negative work being done. It's dissipated energy. Things like friction, heat, and sound, those will do negative work on our system. The next thing is adding water. If we add water to our system, that's like doing positive work. So we add more energy into the system. So negative work is spilling that water out. Adding energy, adding water is doing positive work on our system, increasing the amount of energy that's in our system. All right, so in this example, we look at what happens. This is called an energy diagram. We look at what happens with the energy as it transfers from one type to another. So we start with gravitational potential energy. This dashed line refers to how much energy we start with at the top. And then as it comes down, it's going to lose that gravitational potential energy because it loses height. But in the process, it speeds up, and that's where we get kinetic energy. The kinetic energy is going to increase because we're getting faster. The gravitational potential energy decreases because we're losing our height. And then as this transfers, we get more speed, but we lose height, so we get more energy to transfer. Now you'll notice the amount of gravitational potential energy we started with is equal to the amount of kinetic energy that we gained in the process. And as it moves at a constant speed along a level surface, then we don't have any more energy that is transferred. Notice there's no dissipated energy because we don't have any air friction in the process. So to look at the entire process from beginning to end, it would look like this. So energy transfers from one type to another, and in that process, we don't lose any energy. The total amount of energy stays the same. In this process, we're going to add air friction in here. So that means we're going to include some dissipated energy. That means as the gravitational potential energy decreases because we're decreasing our height, then we have kinetic energy that is increasing. And the reason kinetic energy increasing again is because we're getting faster. But we're also increasing the dissipated energy because we have friction that takes energy out of the system. Now the purpose of this is to show that the amount of kinetic energy added to the amount of gravitational potential energy wouldn't be equal to the initial because we have some dissipated energy. So all of these added together give us our total amount of energy. I have energy that transfers from one type to another, but the total amount I start with is equal to the total amount I end with. So as it goes down, we lose gravitational potential energy, but that goes over to kinetic and dissipated energy. Now at the bottom here, it's going to slow down because we have friction, so that means we lose kinetic and goes over to dissipated. Now the entire system, if we go from beginning to the end, it would look like this. So you can see in the process, we're going to transfer energy from one type to another, but the total amount is going to stay the same in the process, just from one type to another. In this one, we have a book that's falling. We don't have air friction, so as it falls, the gravitational potential energy converts over to kinetic. And then we get down to the bottom where all the gravitational potential energy is going to be kinetic, but once it hits the ground, it hits the ground and stops. So all of that energy is now going over to dissipated. Now, how do I know that? Well, I have no more height and I have no more speed, so therefore all of it has to be over and dissipated. Now, the entire system looks like this when it goes through. All right, so again, we start with gravitational potential, converts over to kinetic until it hits the ground, and then we lose all of it. And the reason we know we lose that dissipated energy is because we hear it. The sound is part of dissipated energy. All right, so now we have an object that starts from a height, and this is a bouncy object, and there is air friction. So as it falls, we have some gravitational potential energy that converts over to kinetic, but it also converts over to dissipated because we have some air friction. You'll notice this last little column here that we have U sub S. That's referring to spring potential energy. The spring potential energy because when that ball hits the ground, it'll bounce. So as it falls, we lose gravitational potential over to kinetic and dissipated all the way until we get to the ground. Once we get to the ground, now it's going to spring, so it's going to stop, meaning we lose that kinetic energy, and that energy goes over to spring potential, but it also goes over to dissipated. Now, as it springs together and stops, then we have some spring potential energy stored up, and then that spring potential energy we get back as it bounces back upward. But in the process, we're still losing energy over to dissipated. So that each of these lines show this is where the kinetic energy was when it started to bounce, and then this is where the kinetic energy is when it starts coming back up. Now, because we have dissipated energy, all the energy is not going to go back over to gravitational potential. We have kinetic that goes over to gravitational potential, but then we have some dissipated energy in the process. And this is why an object that bounces from a certain height can never get back up to that certain height, because we can never have that dissipated energy go back into any form. This is a non-conservative energy, and therefore once we lose energy to dissipated, it is gone and we can't get it back. So the gravitational potential energy can only be so high, and therefore the height can only be so much. We can't get back up to that original height because that original height will require more gravitational potential energy than we have. So the entire process would look like this. All right, so these energy diagrams, they show what happens to the energy as it transfers back and forth, but the main idea is that energy is conserved because the amount of energy I start with is equal to the amount of energy that I end with. So the law of conservation of energy, we're going to start getting into the math now. So the main idea is that the total energy I start with, if I have any work that's done by outside forces, so an applied force would do positive work, or negative work would be done by dissipated energy or friction. If I do any work on the system, that's going to be added or subtracted, and that'll be equal to my final energy. If I have a closed system where no work is done on or by my system, then the total energy I start with is equal to the total energy that I end with. All right, so the energy is either going to be potential or kinetic. Potential meaning spring potential or gravitational potential. And then we have our kinetic energy that it also pans out to. So we have our entire conservation of energy equation. That's all those potential energy, kinetic energy, and then any work that's done, and then that's going to be equal to my final gravitational potential energy and my final kinetic energy, all my potential energies at the end and the kinetic energy at the end. So notice that I start with potential and kinetic energy at the beginning. I end with potential and kinetic energy at the end, and in the process of transferring, I may have some work done. If I don't have any work done, then the total energy I start with would be equal to the total energy I end with. You can see the equations here. The gravitational potential energy equal to mass times gravity times the height. The kinetic energy is 1/2 times the mass times the speed squared. And then the work done is going to be equal to some force that's being applied times the displacement of that force. All right, for our first example, it says a 2.5 kilogram mass is dropped from a 53-meter cliff. How fast will the mass be moving right before it hits the bottom of the cliff? All right, we're dealing with different types of energies because I'm dealing with a changing height, and because I'm dealing with a changing height, I'm dealing with gravitational potential. And at the when it hits the bottom, it's going to be moving. So that means with motion, we have a kinetic energy. So therefore, with two types of energies, that brings us to our conservation of energy equation. So I see here I have initial gravitational potential energy plus initial kinetic energy plus or minus any work that's done in the system is going to be equal to the final gravitational potential energy plus the final kinetic energy. So our first step in this is rather than having this big, huge equation, we're going to go ahead and eliminate, cross out the things that we don't need. So we have height at the beginning, so we're going to have gravitational potential energy at the beginning. But it starts from rest because it's being dropped, so that means our initial kinetic energy is going to be equal to 0. We can go ahead and cross that out. Now in this process, we don't have any outside forces, we don't have friction, or we don't have anybody pushing on it, so therefore we don't have any outside work being done. And then that's going to be equal to the final gravitational potential energy. We're going to end at the bottom, so that means our final gravitational potential energy is going to be 0, but it is going to be moving at the bottom, so we do have a final kinetic energy. So then we simplify our equation so that we just have this. The initial gravitational potential energy is going to be equal to the final kinetic energy. So mass times gravity times the initial height is going to be equal to 1/2 times mass times the final velocity squared. So the first step in this process, again, is to eliminate those types of energies that are irrelevant to our scenario, cancel those out, and make the equation a little bit more simple. All right, so we have our equation. Let's go ahead and plug in our numbers. We got mass is 2.5 kilograms. The acceleration due to gravity is 9.8. The height initially is going to be 53 meters. And then we got 1/2 times 2.5 times the final speed squared. So on the left-hand side, we multiplied that together. You get 1,298.5. And on the right-hand side, you have 1/2 times 2.5, which gives me 1.25. And then we divide both sides by that 1.25 to isolate our variable. That leaves us with the final velocity squared equals 1,038.8. We square root both sides. Square root both sides, and you get this final speed is going to be 32.2 meters per second. So that means that our mass is going to be moving at 32.2 meters per second at the end. This next example, it says a 3.0 kilogram mass is dropped from a 62-meter cliff, and on the way down we have 700 joules of energy that is dissipated. How fast will the mass be moving right before it hits the bottom of the cliff? All right, so we start with the same equation, conservation of energy equation. We got the initial gravitational potential energy and the initial kinetic energy plus or minus any work done is going to be equal to final gravitational potential energy plus the final kinetic energy. Now we start with an initial height, so we have an initial gravitational potential energy, but it starts from rest because it's dropped, so we know the initial kinetic energy is going to be 0. The next part is the work that's being done. Well, we know we have work being done. We have 700 joules of work. Now the question is it going to be positive work or is it going to be negative work? Which one is it going to be? Now dissipated energy, if you remember, dissipated energy does negative work. It takes energy out of the system. So we're going to have our negative for this work. And then that's going to be equal to the final gravitational potential energy. It's going to be at the bottom. So that means we're going to have a final gravitational potential energy of 0. Go ahead and cross that out. And then the final kinetic energy, well, it's going to be moving right before it hits the ground, so we have a final kinetic energy. Now to simplify this equation, we got the gravitational potential energy at the beginning, mass times gravity times the initial height, minus the work being done is going to be equal to 1/2 times mass times the final velocity squared. Go ahead and plug in our numbers. We get 3 times 9.8 times 62 minus our 700 joules of dissipated energy is going to be equal to 1/2 times 3 times the final speed squared. So then on the left-hand side, we do the 3 times 9.8 times 62, get 1,822.8. Subtract off that 700, and then that's going to be equal to half of 3, which is 1.5, times the final velocity squared. Subtracting that 700 from 1822.8, you get 1122.8. Now we divide both sides by 1.5 to give us our final velocity squared is 748.5. Square root both sides, and we get the final speed is going to be 27.4 meters per second. Now what's interesting about this is this started from a higher height, from 62 meters than the previous example, but we end with a lower speed. And the reason we end with a lower speed is because we have this 700 joules of dissipated energy in the process. So our mass is going to be moving at 27.4 meters per second.